All right, so a few announcements from ASQ. If you hadn't heard before, ASQ now offers you the ability to take a certification exam from the convenience of your own work or home. For the last couple of years, ASQ has been offering the certification exams through Prometrics, and you always had to go to their office. But now you have the opportunity to take the exam from the convenience of your own home, again through Prometric. And if you are interested, there's a link here to get more information. And there's also a link at the bottom of the screen showing you if you want to get any continuing updates from ASQ with respect to what are they doing in response to COVID. So a couple links you might want to check out. And speaking about certification, there are some certification exams coming in August. The application deadline is July 10th. So if you're interested in any one of these certifications, you would want to go to the ASQ.org and file an application. A couple updates from the Phoenix section. You've probably heard ad nauseum, the member experience survey. And I just want to say thank you to everybody who did participate in the survey. The survey is now closed. It was open for 2 weeks. So we sent out 630 surveys. That's the number of members who had opted in to receive an email from the section. And of those 630, we had 40 that bounced back, either due to a bad email or maybe there was some type of a security filter, maybe on their work server. So of those 590 surveys then that were successfully sent out, we had 109 responses, or 18% of our membership. So I was hoping for a little more, hoping for upwards of 25%, but 18% isn't terrible, primarily because it was a very detailed and in-depth survey. Depending upon how you answered the questions, you could have seen up to 56 questions, I think it was. So again, 18% is a respectable number. I would have, again, maybe not the best. And remember, as an incentive, we were offering $5 for every completed survey. So that's $545 that you, help to donate to St. Mary's Food Bank, which is a very great need this time of year, especially with the COVID situation and all the people on unemployment and whose other benefits are running out. So a great example of how quality can be an impact in your local community where we all live and work. So thank you everybody who did participate. Our plan then is to do a deep dive drill down analysis the months of June and July. We have some very high level results today, but what I've done is I've asked each one of our officers in the various responsibilities to take a look at those questions that are germane to those areas of concern and to do a drill down analysis. So, for example, we may have asked a question, well, how important is social media as a member benefit? And overall, the answer was relatively low in importance. But if we drill down to maybe take it as a look as a percentage of age, a different age category, or years of membership in ASQ, we might see that our younger people might weigh that a little heavier, more strongly in favor of. So we want to do that type of detailed analysis to really understand all of our members' needs, where are our strengths and where are our opportunities, and then we plan to issue reports to the leadership team as well as to our membership during the month of August. And then September, October, November is when we begin our strategic planning process for the next year. So definitely customer focus, customer input is a very important element of any strategic planning process. So thank you. I just want to give an example of a high-level analysis. At the bottom of the survey was the overall satisfaction. So loyalty type questions. So customer loyalty, customer satisfaction are kind of agglomerated by these three measures of overall satisfaction. Are they willing to recommend the section to their friends? And do they have an intent to repurchase, or in our case, to renew? And pretty good marks. In fact, it's considered world class if you score 80% or higher in each category. So at the, at a very high level, looks like we're doing pretty well, but obviously there are always opportunities for improvement, and that's really what we want to focus in on. The other announcement I want to make on behalf of the section is, again, towards this migration of our members from our ASQPhoenix.org website to our new website on MyASQ. Our ASQPhoenix.org website, the subscription expires November 7th, and we've made the decision not to renew, partly because it is ASQ headquarters' strong intent that every member unit, that is every section, every division, please migrate all of their content, electronic content, to MyASQ. Because MyASQ is designed to be ASQ's primary collaboration tool. And by having every section and every division on MyASQ, it's much easier to navigate from one section to a division to another without having to leave ASQ. So it's a great collaboration tool. To help incentivize that migration, we've come up with 3 levels of reward. So obviously, it's not a big amount, but figure every little bit is probably an added bonus or incentive. So for every member who creates a new profile, that is, you log on to MyASQ and you update your ASQ profile, you get put into a drawing, and every month we'll draw out names of people who joined that month. And we'll be selecting 3 people at random and giving them a $10 gift certificate. Additionally, beyond just creating a profile, if you participate in any existing discussion topic or reply to a comment made on our community site, you have the chance for a $15 gift certificate. And for any member who initiates a new discussion topic, you have the chance to win a $25 gift certificate. And this will be repeated monthly, so from May through December. So how do you participate in those discussions? So once you log into MyASQ and log in with your username and password, then in the right-hand side of the screen, you'll see communities, and you find and select Phoenix section community, and this brings them in to our community site on MyASQ. And you can either go that route or just copy paste this string, this URL will bring you directly to our MyASQ website. And then you see we have a menu bar. You click on the discussions. So this will be the discussions in the Phoenix section. This is what that discussion page looks like. So you have 3 main areas. You have, if you want to post a brand new topic, you can either post a new topic in the general category, which is what this red arrow is pointing to, or you can select an existing topic, and that would be what's in this green box. So these are topics that have already been initiated by somebody, either an officer or one of our members, by clicking on the new topic and then filling out a title and then asking their question or putting their comments. And then once that's in there, that would be initiating one. And then if you have a thought or a reply, suppose you had a thought on internship, or you had something, you could respond to Austin. So Austin, one of our members, initiated this new discussion topic here this month in May. He's looking for somebody who might have a questionnaire or a survey to take the pulse of attitudes towards quality in an organization. So if you have any ideas, suggestions, thoughts, comments, you can reply to Austin's next topic here. So this whole left side would be called the general category. We also have some division-specific categories over here. So you can also click on any one of these, and you could start a new conversation. So many different ways to start a discussion. The reason we're incentivizing discussions is it's a good way to help build engagement of our membership. Hopefully you'll take advantage of that. And the incentive, based on a sample size of 1, seems to have at least made some impact on the number of new profiles. We've been running at a run rate of about 5 or 6 per month. And then we initiated this campaign for the month starting in May. So in May we had 20 new members. So thank you for those 20. And of those 20, again, we drew 3 names to get the $10 gift certificate. So this month for May, we have Julie, Christy, and Robert, who have won that $10 gift certificate. And then Austin is the winner of the 25 for initiating a new discussion. Now, Shruti Shayamani, she's one of our officers. She's our audit chair, and she's also our internet liaison. So she is the person who keeps our websites up to speed. She will be contacting all the winners and asking if your option, you don't have to take the gift certificate. If you'd rather just donate that $10, $15, or $25 to the food bank in your name, we can do that as well. So totally your choice, and Shruti is coordinating that program. Please continue to visit us on MyASQ, because November 1, our old website is no more. And then I think this is my last slide, and I'll turn it over to our guest speaker. Every month, I like to give an update on where we are at with our strategic plan. So back in last November and December, we came up with these 12 strategies that we wanted to concentrate on this year. And we assigned an owner to each one of those. And then the owners to each one of these filled out a project charter. So we had clarity on what's the problem that we're trying to solve, what's in scope, what's out of scope, what's the planned course of action. And now they're working that plan. So you see, first couple months we're a little slow getting on board. We got the project charters scoped in March, and now we're starting to work the plan. We're already at a solid green for a couple of our strategies, so that's excellent. In fact, the survey has been developed, launched, and now we're in the midst of analyzing it. We do have 3 plans that are delayed, primarily due to the whole COVID situation. With the lack of face-to-face, it really is hard to do anything with a community service project, although I'm sure we can get credit with the donations we've been making to St. Mary's Food Bank as a type of a community service. But I think this one we're specifically looking at more of a quality focus, an opportunity to apply a quality tool or method somewhere. The developing a new placement process is delayed here primarily because our placement chair works at Honor Health, and he has been inundated and working very long hours ever since the coronavirus pandemic hit our shores. So understandably, that program is delayed, and it was a lower priority anyhow. And then obtaining division speaker lists is delayed, partly due to COVID, but also because the higher level organization, the GCC, the Geographic Committee, so all the sections report to the GCC, all the ASQ divisions report up to the TCC, or Technical Committee, Technical Conference Committee. Well, after we started this as a project and I was asking for help, then I became aware that those two higher level committees are actually taking ownership of this. So they are gathering the speaker lists from all the divisions, and they will be reporting those down to all the sections. And we wanted to do this so we would have a greater breadth of speakers to draw upon for future program meetings. So, but otherwise, we are moving pretty well. We've got quite a few greens, and I like to just keep everyone up to date of our strategic plan. So, all right, with that, I would like to turn this presentation tonight over to our guest speaker, Eric Moss from Medtronic. The topic for tonight's discussion is predictive engineering, from deterministic to stochastic modeling to confidently develop compelling, robust new products. So if that title doesn't grab you and doesn't sound like a compelling talk, I'm not sure what more we can do, but I think this will be a great talk. A little bit about Eric. He is the Senior Director for Design for Six Sigma and Design for Reliable Manufacturing. Is that right?
Yes. Yes.
For Medtronic Restorative Therapy Group. Eric is responsible for developing and leading DRM's strategic plan and focus for most of the company, and has been the chief architect of Medtronic's Design for Six Sigma Black Belt and Master Black Belt programs. Eric was recognized with Medtronic's Individual Star of Excellence Award for 2012 and has been recognized as a Medtronic Technical Fellow. Eric joined Medtronic after 30 years with Motorola, where he was a co-founder of the Six Sigma methods and a lead Master Black Belt for Design for Six Sigma at Motorola. Eric received his bachelor's degree in biological sciences from the University of Maryland, Baltimore County, his master's degree in biomedical and chemical engineering right here from Arizona State University, and his PhD in industrial and systems engineering also from ASU. Dr. Moss also currently serves as an adjunct professor at ASU. So a little bit about stochastic modeling. Engineers traditionally use deterministic modeling in their tasks, but the challenges posed with medical applications expand beyond deterministic to more probabilistic or stochastic modeling. The melding then of engineering modeling with probabilistic thinking empowers engineers to develop confidence for ourselves, our customers, and not to be mentioned, the FDA, that our therapies are likely to be successful and we will flawlessly meet or exceed expectations over a comprehensive range of use conditions. Predictive engineering starts from measurable system-level requirements translated from voice of customer, exploration and documentation of use conditions, the development of transfer functions for key requirements based on design factors and use conditions, leveraging the transfer functions with probabilistic modeling using Monte Carlo simulation or Bayesian networks to optimize the design and process. So with that, I turn it over to Eric. And Eric, I will make you the presenter here.
Thank you very much. I look forward to clicking share content.
Gotta find your name on the list. There you go.
Yeah.
Change to presenter. All right. You are now the presenter.
All right.
You have your screen up and ready to, there we go.
All right, very good. Hopefully you can see my screen and slide share both.
I can.
All right, very good. So thank you, Quality Bob. So predictive engineering from deterministic to stochastic or probabilistic modeling, developing, robust, compelling new products. I have a little picture there that will make a little bit more sense as I go through the presentation. But let me give a little bit of context. So here's a famous author on the right-hand side, and on the left-hand side, Michael Lewis. You know he's famous because, you know, the font of his name is the same font as the title of the book, The Undoing Project, on the right-hand side, A Friendship That Changed Our Minds. And he wrote it, as I'm going to show you on the next slide, because of the responses to his earlier book, Moneyball, now a major motion picture. And a lot of Michael Lewis's books have become movies, and maybe The Undoing Project that I'm going to speak about on the next slide, maybe that will be a movie in the not-too-distant future. But anyway, going on to the next slide here then, on page 17 of The Undoing Project, Michael Lewis explains why he wrote this book. And so I'm just directly quoting from page 17. And so once the dust is settled on his responses to the earlier book, Moneyball, one response remains more alive and relevant. The author of Moneyball, referring to Michael Lewis, did not seem to realize the deeper reason, the ways in which any expert's judgments might be warped by the expert's own mind, as has been described years ago by a pair of Israeli psychologists, Daniel Kahneman and Amos Tversky. So that kind of piqued Michael Lewis's interest, and then he looked into this a little bit further, and he said, how on earth does a psychologist win the Nobel Prize in economics? Normally, when somebody wins a Nobel Prize in physics, they're a physicist. When they win a Nobel Prize in chemistry, they're a chemist. And of course, when they win a Nobel Prize in economics, they're an economist. How on earth does a psychologist win a Nobel Prize in economics? There is Daniel Kahneman winning the Nobel Prize in economics in 2002. And the answer to those questions emerged there was another story to tell. So what they were talking about, later on, Daniel Kahneman, the winner of the Nobel Prize in economics, wrote a book called Thinking Fast and Slow, and they basically overturned economic theory about how we made decisions. They assumed we made decisions using what they called the rational choice theory. But we are not rational in our decision-making. We are, in fact, predictably irrational because we tend to make decisions using what they call heuristic thinking. That is what, in the title of the book, Thinking Fast and Slow, Daniel Kahneman refers to as thinking fast. With heuristic thinking, that's a way of saying thinking by rules of thumb. If the price is too low, there's got to be a catch. Or, hey, I don't know what to do, but what does everybody else do? I'm going to follow what other people are doing. Or I don't know what to do, but what are the experts telling me to do? And they found that that's the way most people make these decisions, is with a group of documented rules of thumb, heuristic thinking. Thinking slow, on the other hand, is more like what those of us in engineering have learned, which is model-based thinking. We either have, in our models are basically abstractions from reality. Sometimes we have physical models like scale models of buildings or scale models of bridges. Sometimes there are mathematical models like the ideal gas law, PV equals nRT, or Ohm's law, voltage equals current times resistance. Sometimes there's simulation programs like circuit simulation programs or mechanical simulations like finite element analysis. Now I'm going to pause real quickly before I click the mouse going forward. So I actually used this slide. I was asked to give a keynote speech, first at Motorola and then at a conference for reliability. And I have to go to physical therapy every once in a while. And so the physical therapist was asking me, well, what was my talk about? And I started to try, okay, how do I explain it? And I said, well, it's about modeling. And suddenly the room went dead quiet. Modeling. Everybody thought I was thinking about this kind of modeling. Unfortunately, I had to disappoint everybody. I'm not talking about that. I'm talking about a less glamorous version of modeling, engineering modeling, as you see here on the right-hand side. But the point is, the modeling that we're thinking that we learned as engineers is deterministic model-based thinking. And I'm going to try to make the contrast between deterministic model-based thinking and stochastic or probabilistic model-based thinking on the next few slides. But I'm going to have a quote from Daniel Kahneman and Amos Tversky about that book that was written, The Undoing Project. Here's a quote from 1972 from that collaboration. Man is a deterministic device thrown into a probabilistic universe. So I'm going to talk a bit about deterministic versus probabilistic, and I'll use that quote another time later in this presentation. But what we're doing is we're going to take the deterministic model-based thinking that the engineers learned in college and make it probabilistic. And one way we'll do that is with Monte Carlo simulation. I'm showing you an image that will make a little bit more sense later on in this presentation, where we're going from a deterministic model to a probabilistic model using Monte Carlo simulation. And the other part we'll talk briefly about is Bayesian methods, and this is a slide you'll see later on of Bayesian methods. And both of those ways of taking deterministic models and making them stochastic or probabilistic, which allows us to deal with uncertainties. So what do I mean by that? Well, Monte Carlo simulation, before I go on, that's one of the methods. That's what I'll talk about first. That was developed as part of the Manhattan Project during World War II. to develop the atomic bomb. The Manhattan Project had ENIAC, one of the very first computers in the world. And over here you see the proud father, John von Neumann, with his cute little baby ENIAC. That was used as part of the Manhattan Project. So what did they use ENIAC for in the Manhattan Project? Well, John von Neumann brought this man over here, Stanislaw Ulam, to run a series of simulations on the achievement of critical mass. Basically, just a brute force method of trying this combination, this combination, this combination, thousands of times to see how you could achieve critical mass to have a nuclear explosion. And he named this technique Monte Carlo simulation, and he named it after the probability of winning with the randomness at Monte Carlo casinos in Monte Carlo in Monaco over in Europe. So, Monte Carlo simulation, just a little one-page summary, is a probabilistic or statistical modeling method, some of you are familiar with, to estimate the distribution of our outputs, our Ys, and those outputs can be project schedule, they can be cycle time, they can be on-time delivery, the probability of on-time delivery, they can be financial results, and a lot of people use Monte Carlo simulation for financial results, either personally for their own personal results or as well for the business, or performance, which is what we're talking about as engineers, or reliability, as many of you would be interested in. And so here I'm showing an example of a Monte Carlo simulation for an engineering parameter, totally rated power out of the antenna of a cell phone, and the right-hand side, the sensitivity analysis that shows. So basically the outputs of Monte Carlo simulation are the mean, the distribution, the spread, the probability of your forecasted output that I'm calling your Y, the level of confidence of the product's performance, in this case, this little circled area at the bottom, 74%, and identifies with that sensitivity chart on the right-hand side which of the factors or X's have the biggest impact on the variability or uncertainty of my output, my Y. So one way of going from deterministic modeling to probabilistic, you take your deterministic model, let's say it's a what we call a first principles model, an equation you get out of a textbook, like Ohm's law, voltage equals current times resistance. And with a little simple algebra, current equals voltage divided by resistance. So maybe in a lab, they give you a 1.5 volt battery, as you see here. I'll go ahead and see if I can get my little pointer going here for a moment. You have a little battery, 1.5 volt battery, you put it across the 1 kilo ohm resistor, and according to Ohm's law, you should have 1.5 milliamps, and you check your ohm meter, and it looks like 1.5 milliamps, and you write it your engineering report. But you take that probabilistically, well, it's not exactly going to be exactly 1.5 volts on that battery. It's going to have some distribution about it. It's not exactly going to be a 1.00000 kilo ohm resistor, so you allow some variation about that. And you're not going to be able to exactly read the measured current. There's going to be some measurement error due to parallax or whatever else. And so your actual distribution is going to be a distribution around 1.5 milliamps, as you see in this bottom chart. And that's what you can model with Monte Carlo simulation. You can take a deterministic model and make it probabilistic. But the first time I ever heard about this concept, and I'm showing my age here, I'm older than most of you, maybe all of you, was when I was a kid, and both my parents were smokers. So the smoking causes lung cancer controversy. So back in 1964, the Surgeon General of the United States, Dr. Luther Terry, made an amazing comment. He said, smoking causes lung cancer. And that had a big impact. In fact, you know, most of you people nowadays, we would all be living, I was living in a smoke-filled house. Both my parents smoked, most of their friends smoked. And it was a very common thing. Nowadays, a lot of people's lives have been saved because of that pronouncement by Dr. Terry back in 1964. The amount of smoking has gone down considerably in the decades since then. But when the Dr. Terry came out with that statement, smoking causes lung cancer, it confused my parents. And I was a little kid listening in to my parents talking to their friends, and they were confused. They said, we smoke, we don't have lung cancer. How can the Surgeon General say smoking causes lung cancer if we smoke and we don't have lung cancer? They were thinking in terms of deterministic causality, that if you drive over a nail, you will 100% get a flat tire. He's 100% certain. That's not what he was referring to. Dr. Terry was not referring to deterministic causality. He was talking about probabilistic causality, that the probability of death from lung cancer for heavy smokers was more than 20 times higher than the probability of death from lung cancer for non-smokers. And they determined that probability ratio using Bayesian methods, which I'll talk about a little bit later on. So the idea here, and this was in the abstract that Quality Bob mentioned a while ago, predictive engineering is basically the melding of engineering modeling that engineers learned in college with probabilistic thinking. And one way of doing that is with Monte Carlo simulation, and I'll talk about that in the first few examples. And another way is with Bayesian methods, which I'll talk about a little bit later on. So basically over here, and this is actually the first definition for design for Six Sigma, is this diagram. So over here in the middle here are a bunch of your requirements, and you have a subset of the requirements, your key parameters or critical parameters, and you flow them down to the subordinate requirements, the X's and N's, the factors you control, X's, and the noises that you don't control, and you get distributions of the important factors. We may do like a fractional factorial experiment. We might use that as an example in a little while. And you get the distribution of the important factors, put them through your engineering model with Monte Carlo simulation, and you predict your distribution of the outputs and see if it's good enough. And that's one way of Monte Carlo simulation. So I'm going to show an example here for Micra. Medtronic's Micra, you see a picture of it right there, was one of the very first new products at Medtronic to use this predictive engineering approach rather extensively. And I'll be showing, one part in detail and a few other aspects of Micra that where we use predictive engineering. So basically, here's the requirement flow down. We start at the top with the voice of the customer. At the top here, let's see if I can grab my, we use a voice of the customer up here, and we translate them into measurable system requirements. So to have minimized the size of it, we have the volume less than 0.75, and that drives down to a length and radius requirement. Minimize the probability of expanding it prematurely, and that drives down reliability requirements. This is the real requirement, reliability flow down for Micra at the time called PLIF, percutaneous leadless pacemaker system. And then requirements on the pacing voltage and the requirements of the access to diagnostic information for the physician. So I'm going to show down one of these flow down requirements, the fixation, and this was a predictive engineering design for Six Sigma project done by Arshad Al-Fokaha. And you see over here a picture of Micra at the end product at the right-hand side. So showing the microfixation, and hopefully this video will show a little bit. This is a video done by Medtronic in conjunction with University of Minnesota. And you see there, they're attaching it to the heart. It's a pacemaker that goes inside the heart. Here they're doing it with 4C with a pig. And I'd say that the first place they put it into the heart is not a good spot for pacing the heart. So they have to recapture it. Well, when they recapture it, they don't want to tear the heart tissue, and that sets an upper step limit of 3 newtons of attachment force, fixation force, we'll call that. And then they reposition it elsewhere, and now this is the right spot, and it's going to pace the heart for years and years and years. They need to make sure it stays in place, and that's going to impose a lower spec limit of 2 newtons of fixation force. So then they figured out a way to model that fixation using finite element analysis. The specific tool was called Abacus. So you see there, they were doing some simulations on the left hand, and then they were comparing it to reality done with porcine heart tissue, pork heart tissue on the right hand side, and try to get good calibration, reduce the model error, the difference between the model and reality. And then they flow down, so you see on the right hand side the requirements, lower limit of 2 newtons, below that it might come loose, upper limit of 3 newtons, above 3 newtons might not be able to be repositioned without tearing the heart muscle, heart tissue, and then they flow them down to a bunch of requirements that could be significant. That's called requirement flow down. So one way of doing a requirement flow down is with a P diagram, a parameter diagram, and the control factors that we're going to talk about in this example are the time thickness, the length of this time, the length of the time, the thickness of the time, how thick it is, and then its curves, so the radius of curvature of it, the time that attaches it to the heart. And we intend the result is safely attached, and we don't want to have detachment or damage to the heart tissue. So basically, if you just had a one-factor experiment, I'm showing you a picture of the time over here schematically, cross-section over here on the right-hand side. If you just had one parameter, time thickness, you might do like a student's t-test, compare the value at a low level of thickness and level at a high level of thickness. With 2 factors, like say thickness and length, now it's represented geometrically by a square. Thickness is one factor, length is the other factor, and you have 4 possible combinations, 2 to the 2 factorial design. With 3 factors, which is what Arshad Al-Fokaha, the black belt, did on this, it'll be represented geometrically with a cube, so these 8 points over here. And then they later added the center point, which I'll talk about shortly here. So basically, these are the original 8 runs that he ran on the simulator. So these are thicknesses, length, and radius. Each of these rows, 1 run through the Abacus simulator, and the simulator told them what the pull force would be, 8 newtons of pull force, compared to the spec limit of 1 to 3 newtons. And this is showing that geometric representation over there. So then when we analyzed the experiment, turned out that factor B, length, was not significant. Factors A and C, the thickness of the time and the radius of curvature, turned out to be significant. So we reduced the equation, and you see it over here. Here's a step-by-step reduction of the equation. Step 1, all the factors are in there. Step 2, we got rid of thickness, time, length interaction. Step 3, we got rid of thickness and length overall. And now we have our simpler equation. over here, and that became the equation in encoded units that we're going to use with Monte Carlo simulation if there is no curvature. Turned out there was curvature, so we had to augment it. We added the center point that detected the curvature. We augmented it, added what we call star points, these 6 points in over here, and they're represented by those red circles. So augmented design to allow us to come up with a quadratic or polynomial equation to represent fixation force versus thickness and radius of curvature rather than a linear function. So now we take that equation that we got from that response service modeling that's called, with that, original DOEs augmented with the star points, that's called RSM. That equation we got from that, we bring in the variation of thickness we were getting manufacturing, the variation of radius of curvature we get from manufacturing, plugged it through the equation, and predicted what our distribution would be compared to our spec limits of 2 to 3 newtons. And you see, initially, the initial design would have been below the lower spec limit of 2, would not have been good for human usage. And so we optimized it, and you see over here, we were able to get really good CPK and really high confidence in the fixation force being within the spec limits of 2 to 3 newtons. So that was just one part of the reliability modeling, and that was actually hazard patient harm, that fixation force. We also cared about the largest part is the actual simplified version of the reliability flow down for micro. 368 ppm per month corresponded to 97% reliability at 7 years. And the biggest part of it was longevity, the battery life, where it would be pacing the heart. So we looked at the longevity and we built a Monte Carlo simulation for that. So I'm show you kind of a diagram and a view of our Monte Carlo simulation of our longevity and the actual results from the longevity for, in this case, up to 10 years here and 15 years over here, the longevity. And we were able to optimize the design of the circuitry to reduce the amount of current being consumed to extend out that longevity so this would last years and years and still do a good job of pacing the heart. And then similarly, we had other requirements, like the requirement from the physician wanted to be able to get data from this pacemaker inside the heart, and that put a requirement on the antenna for the medical telemetry. So Ryan Vogt worked there. He came up with a P diagram, worked with the supplier, did RSM, this you see over here, and results from the RSM at the bottom, and then ran it through Monte Carlo simulation and then optimization and got good CPKs for all the requirements for the antenna. And then for the actual pacing voltage, that was largely set by a regulator. So we had 4 requirements on the regulator, the amount of current being drawn, so that would help with our longevity. And then the output voltage and the stability and ripple that flowed down to control factors and noise factors. So an intern named Brian Foss worked with experienced engineer Naveed Alam, and they built this model of it, bringing in the noise factors shown in red, the N-channel and P-channel threshold voltage variation, and the amount of loading, how much current you were pulling out of this over the life. And the 4 requirements, the output voltage, the current being drawn, stability, and ripple. And initially, the red shows it's outside of the spec window initial design. And so they optimized it and got really good CPKs on everything. So basically, that melding of engineering modeling with probabilistic thinking that I call predictive engineering, I'm showing the example of using it with Monte Carlo simulation for various aspects of this micro project. Similarly, we did some things on the Bayesian side. So we didn't stop with the microfixation, just making sure it was good enough. We also wanted to make sure there was very low probability of major harm. So we built a Bayesian belief network with an outer loop and an inner loop of things that would stress those times and cause things like single-time fractures and two-time fractures and things like that. And we looked at the risk of harm to the patient, minor harms and major harms. And you see over here on the right-hand side, using the Bayesian network, we actually calculated the probability of problems like pulmonary embolism, harm from extraction. We calculated the probability of death for the patient, the probability of infection for the patient, and we minimized those probabilities. There was also a probability, this pacemaker that goes inside the heart actually detects the person's movement. If they're walking, if they're sleeping, if they're running, if the heart needs to be paced at a different rate depending on that. And we have an accelerometer that was going inside the micro pacemaker. And if it got stuck, it would no longer correctly detect the person's motion, and it would not appropriately pace the heart. And that would be harm to the patient as well. So we built a Bayesian model using a tool called a Heuristic for that, for the probability in vivo in a patient, that we will actually have this accelerometer getting stuck in place and no longer measuring accelerometry. And we were able to show under the actual use conditions, basically about a 12 in a billion chance that would happen. And we figured that was probably acceptable, but nonetheless, we worked with our supplier to reduce that probability even further. So we shared all that with the FDA, some of those projects, and I'm just showing you a subset. There were other projects done as well. But based on all this predictive engineering DRM work that was shared with the FDA agreed to reduce the size of the clinical trial in half, from 1,200 down to 600 patients. And that was kind of a remarkable thing. This is a totally new kind of pacemaker. Never, there's no predicate pacemaker like this that goes inside the heart. And they reduced the clinical trial in half based on all the outstanding predictive engineering work we did. And basically, Micro came out. It was wonderful. And U.S. News and World Report, Science Fiction becomes Science Fact. 2016's biggest achievement in medicine, #1, wireless leading pacemaker, the first leadless pacemaker manufactured by Medtronic. So Micro was named the 2016 biggest achievement in medicine by U.S. News and World Report. Our first product using predictive engineering and Medtronic also was the product of the year according to U.S. News and World Report in the medical field. And it got to market 6 months ahead of schedule in the European Union and in the United States. So the predictive engineering actually accelerated our time to market, largely because we reduced the clinical trial in half, but also because we didn't have to do any redo loops. We had confidence in our product as we were developing it. Here's another example for another device. This is for the nervous system, we required medical telemetry, so we call it the TEL-N circuitry, medical telemetry. It uses amplitude shifting. One is a high amplitude, the 0 is a low amplitude. And we have 4 key requirements. Detect threshold had to be in a range of 3 to 8 millivolts. The current drain, because we want to have long battery life, had to be less than 1 microamp. The turn on time and turn off time, the responsiveness had to be less than 15 microseconds. And so, in this case, Chris Ambry did the DRM Black Belt project on this. He started off with design of experiments, response service modeling, and did multiple response optimization. His 4 responses: detect threshold, the amount of current being drawn, IDD, the turn on time, turn off time, and he found 6 design factors shown over here, and a couple of noise factors. And so we ran 2 to 6 times 1 on the circuit simulator. I'm showing you an electronic example over here. So on a circuit simulator, and it turned out some of the factors weren't so important. Actually, it turned out 4 factors were important. So I added 8 star points and a center point to make it a central positive design, so we could get a polynomial function. And you see over here for each of the 4 responses: detect threshold, the current being drawn, turn on time, turn off time. We've got a quadratic equation for each of those. So with each of those quadratic equations, now we can co-optimize meeting all of our requirements, all 4 of these requirements: detect threshold, IDD, turn on time, turn off time. And so you see over here response surface where detect threshold is a function of a couple of the parameters the designer has to work with. Here it is for the current being drawn as a function of a couple of the other parameters. Here's the turn on time and the turn off time as a function of the parameters. But that's kind of a deterministic model at this point. We wanted to add Monte Carlo to bring in the uncertainty of the manufacturing variations in this and make sure it would be robust against manufacturing variation. And so we did that with a methodology called yield surface modeling that I actually have a patent on. So we have a detect threshold yield surface over here. Over here is the IDD yield surface. Here's a turn off time yield surface. Here's a turn on time yield surface. We multiply them together to get a composite yield surface. And there's where we have, and see over here in this flat area, this is where we can get 100% yield. And that's where Tigger likes to dance around and flip up and down on his tail. So that's where we have robust, stable yield. And with the white cliffs of Dover all around that. So that's how we were able to optimize the medical telemetry for a neuro device. And this is kind of showing the CTK's, the design on this, a very experienced designer, Chris Ambry, spent weeks trial and error just as a comparison. And after weeks of trial and error, the best CPK he got on detect threshold was 0.94. He wants it to be greater than 1. The best CPK on IDD he got was negative 0.92. We want it to be greater than 1. It's a negative number, really, really bad. Turn off time, the best he got was 0.51. You want it again greater than 1. Turn off time, 0.65, wanted it greater than 1. So we did this optimization, this stochastic optimization, probabilistic optimization. CPK went from 0.94 to 33 for the detect threshold, from negative 0.29 to 1.4 for the current being drawn, from 0.51 to 2.8 for the turn on time, from 0.65 to 1.3 for the turn off time. So co-optimized all of them and made it ready to go into production with high confidence. And this is kind of just showing you diagrammatically. These are the 4 requirements: detect threshold, IDD, turn on time, turn off time. Call them the key parameters. Flowed them down to the requirements on the left-hand side. Got the distributions of them. Came up with that circuit simulation and DOE, followed by response service modeling for these multiple responses. Got those quadratic equations for each of the 4 responses as a function of these inputs, and was able to co-optimize them. And this is the after. the distributions of each of them afterwards and very high TPKs afterwards. Here's another example. This is a product that's used in operating rooms called StealthStation S8. The previous version, its predicate product, we call it, was StealthStation S7. And in this case, we had, when Quality Bob introduced me, he mentioned that at Medtronic we called Design for Six Sigma DRM for design, reliability, and manufacturability. And in this case, on StealthStation, we had a total of 5 black belt projects. I'm showing 3 of them over here. Even Patel did one of our software DFSS projects or software DRM projects, trying to use DFSS methodologies that I've been talking about to optimize the latency, to minimize the latency, the delay between the surgeon doing something and it appearing on the visual display, as we'll see over here on the right-hand side. So we did P-diagram over there, the response service modeling, and then Monte Carlo simulation. So the before over here, the eye can detect greater than 250 milliseconds latency. They detect that delay, and you see an awful lot of it, 51% of the time it would have been greater than 250 milliseconds. But by optimizing it using the stochastic optimization, it was getting it to only 5% of the time would surgeon even be able to notice the latency. On the reliability side, we did a use condition matrix and tried to look at all the ways this product could be used or misused or abused or whatever else, and also looked at complaints on the predicate product, StealthStation S7, and basically used it to optimize reliability. And as a result of that, the predicate product, StealthStation S7, had a mean time between failures of 1.9 years. We essentially doubled it to 3.9 years with StealthStation S8. And then on the manufacturing side, we applied these methodologies to how we manufacture it, and for the first year alone, we saved roughly $500,000. So we came out with this product, and it's been a real success, and it's been taking off in the marketplace pre-COVID and still doing pretty well with COVID. Interestingly enough, we were approached by Hollywood, and they said they were coming out with a movie, Dr. Strange, so they took an early version of StealthStation S8. So in the movie StealthStation S8, where Dr. Strange is still a doctor and is working in surgery, they actually lined up behind him some StealthStation S8, so shown in the early scene. So they took everybody at the site in Louisville, Colorado that worked on StealthStation S8, and they all went to the movie theater together to watch Dr. Strange for that 5 seconds where they showed up, StealthStation, their product showed up on the screen. Over here, this is another product. This is neural stimulation, spinal cord stimulation for chronic intractable pain that emanates from the spinal cord. So this is putting electrical pulses into the spine, into the nerves in the spine to reduce pain. And so we gather the voice of the customer here on the left-hand side over here. We also look at complaints with the predicate product, the restore sensor, and a lot of the problem was about recharging. This is using rechargeable battery and how long it takes to recharge and everything else. So, we use those inputs and our requirement flow down in predictive engineering. On the design side, we made sure we met a mechanical requirement of dropping, being able to hold up being dropped and everything else, after reliability requirement, as it turns out as well. On the reliability side, though, we reduced that recharge time from the predicate product 4 to 6 hours to about an hour. And we did a biothermal, make sure it wouldn't hurt the patient, that faster recharge would not cause any harm to the patient over the range of use conditions. And then we built an Intellis reliability model that helped with the reliability, and that was a Bayesian model, which I'll show a little bit about it on a coming up slide. And then similarly to the StealthStation S8 story, we also did on the manufacturing side, and this was the highest yield at launch we've ever had out of that part of Medtronic. It's usually been like 50% yield or 40% yield. When this launched, it was 97% yield. Using this predictive engineering method. Over here, you see a use condition matrix. When Quality Bob gave my little introduction, we try to be comprehensive in our use conditions. We assume Murphy's Law. Anything that can go wrong will go wrong. So you can't see the details here, but over the life cycle of the product, we look at all the types of use conditions and look at ones that aren't relevant. They're the ones in gray. The ones that are relevant and we've taken care of, they show up in green using predictive engineering. The ones still you have to do at this point in time show up in white. And so very clear to the people what they still need to work on before we launch the product. So at the point when I took the screenshot, we were at 94% use condition comprehensives. When we launched, we were at 100% use condition comprehensiveness to prevent anything due to a misuse condition, which, by the way, most of our field corrective actions have been due to misuse conditions. So that melding of engineering modeling with probabilistic thinking is called predictive engineering. And I've shown you a couple of examples of Monochrome Stimulation, a little bit about Bayesian methods, and showing some examples of how we're using that. Taking it from the engineering modeling, our engineers kind of love it because they're already used to engineering model, and now we're taking it a step further, augmenting it with Monochrome Stimulation, Bayesian methods, or so forth, and it just takes it so much further and gives them even more power in the tools they already learned in college and they've learned on the job. So, I guess, here at ASQ, many people are interested in reliability. So I took a few slides from a presentation that we gave to our Chief Quality Officer, Noel at Medtronic. So I used a picture, a little screenshot from National Lampoon Christmas Vacation. So the system is only as reliable as its weakest link. So reliability is intrinsic, a predicted metric. So predictive engineering is very appropriate for it. And if you look at reliability and the definition of reliability, reliability is the probability of successful use over the years or the number of cycles that it's being used. So, and as Kahneman and Heuristic talked about, thinking about probability is not comfortable. In fact, I'm bringing back that quote. Man is a deterministic device thrown into a probabilistic universe. We tend to think deterministically and point fingers when things go wrong, but our universe, and especially the medical device universe, is a probabilistic universe. So the impact of reliability for medical devices. So I joined Medtronic in 2009, and this was very much on everybody's mind. This was a fresh wound in everybody's mind. In October 2007, Medtronic voluntarily recalled the Fidelis lead. And you see there the impact on the stock price of Medtronic shown in blue compared to some other medical device companies, Boston Scientific and St. Jude at the time. And there's our date over there, and there's that big drop. So Medtronic's stock dropped 11%. The value to the market dropped $6 billion basically overnight due to that recall of Fidelis lead due to poor reliability. So I joined Medtronic a couple years afterwards. This is very much weighing on everybody's mind. I worked for my boss in Chandra Subramaniam for about a year in Tempe, Arizona, and then he gets promoted and he moves up to Minnesota to take over R&D for the Cardiac Rhythm Heart Failure Group, the group that makes the pacemakers and defibrillators, including this lead. And he asks me to come up and help them out for about a year. So for about a year, I'm helping out, I'm visiting each of the different groups. And I go to the group that was involved in this Fidelis lead. They're called the Therapy Delivery Systems Group. They're the one who make the leads. And I spent about a day and a half, almost 2 days with the team there. And at the end of the time, the management team pulled me into a room and they said, so Eric, now that you've met with our teams for about 2 days, what do you think? And the words that I said, and I'm going to try to be as verbatim as I can be, I said, organizations like people often have personalities. And if I was to describe the personality of your organization, the term that comes to mind is PTSD, post-traumatic stress disorder. And they all kind of stared at me. And I said, even if I didn't know it, I could tell this is a group that had the Fidelis recall. It's weighing on everybody's mind. Everybody takes it personally. And I guess it's good that you're taking it personally, but it's holding your organization back because there's no way for them to go anywhere with this. Everybody's just avoiding the topic of this major disaster of the Fidelis lead recall. And so they talked among themselves for a few minutes, and the leadership team said, so Eric, what would you recommend? I said, rather than avoiding the topic, I would suggest confronting it. I would take your team and have them take the data they had when they released Fidelis in October 2007, or whatever the time frame when they actually released it. Take the data they had, they released it, and look at it again through a predictive engineering lens. And that is what they did, and it is actually a published paper. So they built a reliability modeling, a basic reliability model for the Fidelis lead and compared it to a good lead called Quattro. So this is reliability or survival on the y-axis versus years for the Quattro lead and for the Fidelis lead. And over here, this upper right, they would have predicted the recall if they had used Bayesian methods on the data they had when they released the products. And so now they've written up as a paper, fracture prediction of cardiac lead medical devices using Bayesian methods, published in Reliable Engineering and System Safety back in 2014. So they actually published this, and they've learned from it, and ever since then, we're using Bayesian methods to predict the probability of failure and the probability of survival for our new products in Therapy Delivery Systems group. And interestingly enough, that group that the heads were down, that they were ashamed of Fidelis lead, that group is now co-authoring papers with the FDA. That same exact group is now co-authoring papers over here. Here, incorporating virtual patients into clinical studies by Adam Himes from Medtronic in that group, Derek Haddad from Medtronic, these are both year on black belts, he possesses black belts at Medtronic, working with 3 people from the FDA. We're co-authoring papers. This group now is holding their head high. They're now the stars of working with the FDA of how to do things right. So the FDA has been very, very supportive of this and very receptive to these theorem approaches. They even quoted in one of their papers back in 2011. Design for Reliability Manufacturing quoted in one of their papers. So as I said, we're actually now co-authoring papers. I just showed one example. Here's another article, Incorporation of Stochastic Engineering Models, Probabilistic Engineering Models, that's Predictive Engineering, as prior information in Bayesian medical device trials. If you know about Bayesian theorem, you know there's a priori and a posterior. That's the a priori information. And you see, Terikadad, theorem master black belt, GFSS master black belt, Adam Himes, theorem black belt, co-authoring with 3 people in the FDA. So and this is the same group that was holding their heads down, that was having post-traumatic stress disorder from the recall of the Fidelis lead they put out there. They're co-authoring papers, and they're the ones who worked on that on the leads, on the times and the optimization of the times for micro. So types of reliability for medical devices. You got single-use reliability. I'll talk about that just for a moment here. Reliability over time, I'll just go back and refresh that a little bit. You saw the example on micro a little while ago. I'll show you a little bit more about the Intellis. I'll show you a little bit about a review of what we did with Cell Station S7. I won't talk anything about software reliability given our short time. So single-use reliability here, and actually I'm showing you a little animation on the left-hand side. But on the right-hand side, this is a plasma blade. This is basically an electrified scalpel. It actually cauterizes, as you cut tissue, it cauterizes the area. And so we built a Bayesian belief network using a Heuristic for the reliability of it. And you can actually see the results over there. So it's 98.9% reliability, as you see over here. And then similarly over here, this is for solitaire, for stroke, kind of roto-rooter for stroke. If you have a clogged blood vessel in your brain, you go in there with this mesh and then pull it back out. And we built we decided to make it easier for people, so I built a way of doing this in Excel to be able to predict the overall single-use reliability for its one and only use, and then what it's most sensitive to, the sensitivity analysis of that. For reliability over time, for implantable devices, you saw the example for micro. For Intellis, that was done using Bayesian methods by a lady who worked with me, Yan Lu, Intellis reliability modeling. Here's your model of Bayesian belief network for it. It was done in a tool called the Heuristic. So she brought in all the reliability, was able to show 95% confidence of 95% reliability, or 95.5% reliability, and was able to optimize it as well. And then she was able to then verify it, validate it with about 1/7 of the normal sample size, a sample size of 97 versus 748 if you use traditional methods. So the Bayesian method actually saved us time and sample sizes. Reliability over time, I showed you a little bit of this earlier on for the Cell Station SA, the use condition matrix for that, and then the parade of complaints from the predicate product, and then built a reliability model and then optimized the reliability model. And again, we doubled the mean time between failures, and it's doing wonderfully. So that's kind of my quick little presentation. Predictive engineering for deterministic to stochastic modeling, develop compelling new products. Right-hand side, you see some of the examples I talked about, Micra, Cell Station SA, the Solitaire, the Intellis, and some products out when I was at Motorola doing this, helping out with the Amazon Kindle display and working on a police radio. So at this point, I guess I'll pause and see if there's any questions or comments for me.
So I've gone ahead and unmuted everybody. If anyone has a question, please feel free to ask Eric. I have a question, Eric. So for our members here in the Phoenix area, and I've only lived in the area for 5 years now, are there any recommended vendors you might suggest for anyone interested in learning more about design for Six Sigma or Bayesian methods?
Well, thank you for the question. For design for Six Sigma, I have to be a little bit self-serving here. So I wrote a book called Applying Design for Six Sigma to Software and Hardware Systems, published by Prentice Hall, so you can get that on Amazon. That would be, of course, my recommended book, not that I'm an unbiased person on that. In terms of Bayesian methods, and I'm going to step away for a second and grab the book really quickly here so I can have it in front of me. So the book I would recommend is called Risk Assessment and Decision Analysis with Bayesian Networks. It's by 2 professors at University of London, Dr. Norman Fenton and Dr. Martin Neal. So and it's a great book, and it comes with, you know, the examples go with a software package called the Heuristic that the authors created. And so as you go through the book, and the book is very well written, a lot of entertaining examples, fun examples, entertaining and realistic examples, but they also, they work out all the examples in the Heuristic so you can actually play with the examples, build the examples, work with them as you go through the book. So if you want to learn Bayesian methods, that would be the recommended book, Risk Assessment and Decision Analysis with Bayesian Networks by Norman Tesler and Neil, which you can get on Amazon. And then Jan Lu, who I mentioned a little while ago, she studied with me, she worked with me. She's written a book, and I'm seeing if I can find it here. Yes, so Jan Lu wrote a book, Practical Applications of Bayesian Reliability, that have some mostly medical device examples because they're examples straight from Medtronic. So those are some of the books I recommend.
Okay, thank you. Any other questions? I know many organizations. Yeah, go ahead.
Yeah, hey, Bill, Eric, I should say, I had two quick questions for you. One, just a quick comment. I actually spent time at Motorola myself in the semiconductor group in Austin. I was in Phoenix several times, doing a lot of work with the semiconductors and whatnot. I had a question about your DOE, which you had set up. Just a basic question. When you you had those three, I guess, parameters that you were evaluating, how did you determine the highs and the lows, if you will, for those for those settings, or for those parameters, I should say? Did you use customer spec limits first of the procedure to start with, or was it just tribal knowledge, or?
Well, no. So you know, this is a totally new product. So there wasn't anything predicate. There wasn't any real tribal knowledge. They were building these times, and so you know, they knew that the dimensions had to go into the body and into the heart, and so they knew the dimensions to be able to get it through the blood vessel into the heart and the area. So that put some constraints on the length and then they basically explored various time thicknesses and length with a little bit in the lab when they were doing studies, trying to get the fixation force studies. But then the original experiment, in this particular case, the original range they came up with for the highs and the lows was working between doing studies with porcine heart tissue, with pork heart tissues, and with different attempts to make times and trying them out. And that came up with the spec limits initially. And it turned out they were in the right range. They were able to optimize within the inner space. I have another example actually at Motorola, where the original space, it was for a nanotube display, where the original space was not in the right space, so they came up with wrong values of the low and the high, but nonetheless, they found the direction where the optimum lies, and they were able to use the path of steepest ascent to move to a new region and run the DOE there. So if you start in the wrong spot, you can still maybe get something out about, see where the direction is, and move to the right region.
Absolutely. Okay, great. Thank you. And the last quick question was, you mentioned we did that finite element analysis. In my grad school days, I'm a mechanical engineer, so we did that. We used that in grad school a little bit. Yeah. So we use a tool called ANSYS, ANSYS. Have you heard of that tool before?
Yes, ANSYS, yes. A lot of people use ANSYS also. Some people, you know, at Medtronic, we don't have any real standards. Some people use ANSYS, some people use Abacus. I think like there are one or two other tools that other people use as well.
Okay. All right, great. Well, that's all I had. Thank you.
Thank you so much.
Thank you.
This is Bud Johnson. I have an observation and a question. The observation is Bayesian stuff, Bayesian analysis in my history has been used oftentimes for Mercedes and a couple of other people. A lot of times they call it degree of belief. And I don't, yeah, it's based on prior knowledge of a lot of the components and things like that, how they'll react to stuff. The question I have is the tools you're showing up, designed for reliability tools or signal tools, however you want to put it, need to fit into a gated process of some sort, I would think. Is your presentation, or can you delineate where these tools reside during the gated process? For instance, the use conditions, that will be almost immediate in the early production or early design of the project.
Yeah, thank you, Harold. Yeah, we have what we're using in in the restorative therapy group of Medtronic, we call it ID2MR, which stands for ideation to market release. And so, yes, in phase 1, we're primarily doing like the business case kind of things. And phase 2, we're trying to get like requirements at the system level. Phase 3, the third stage of ID2MR is where we flow down the requirements and we get our use condition matrices initially, and then we update it during the product development in what we call phase 5. So we look at the use conditions basically twice. We have our first use condition matrix in phase 3 shortly after we have done the requirement flow down. But we try to engage with the physicians to see their range of use conditions, make sure we allow for everything, because I think I mentioned, we assume Murphy's Law. Anything that can go wrong will go wrong. Any use condition we miss can lead to a field corrective action or a complaint, and in fact, they usually do. So that's basically what we do.
I've been graded on the number of field reactions or field complaints that we've got in new projects, simply because I was the reliability guy. And what I found was that you had to be able to, using your word, predictive, you had to be able to predict the reliability before you ever started the project and identify those engineering tools that would get you there. I think I'm learning quite a bit from you. I've also been working with a Motorola engineer extensively for the last 4 years, but he's a Marine and doesn't behave very well. So I thank you very much for.
Thank you. Thank you. Thank you so much.
Hi, Eric. This is Vic Nanda. Thank you so much for the presentation tonight. It was it's incredible. I've worked at Motorola too, and now with Nokia, and I think there's tremendous potential in companies to leverage these kind of techniques. We do a lot of this Monte Carlo simulations and things like that, but you really showed how you can use it for a competitive advantage, and demonstrate with all your analysis how reliable these products are, and even expedite FDA decisions. So that's really incredible. I'm kind of curious, is this pervasive throughout the company, this kind of reliability modeling, this DRM program, or is it just you have some senior leaders who are champions, like in the RTG group, who are advocating for this?
Well, so RTG, the group I'm in, is the strongest right now, and that's partly because of what you were just mentioning, Vic. The leadership of my boss, Chandra Subramanian, that he really drives this. But it is a company-wide program. Our CEO who just retired, Omar Ishrak, PhD in electrical engineering, very much, really bought into DRM, really drove it across the company, expected it for all new projects, as did our chief quality officer, who also recently retired, and our incoming new chief quality officer and our new CEO, Jeff Martha is our new CEO, and Noel Kalan is our new chief quality officer. They're both very strong advocates of DRM. So we have it across all of Medtronic, but some areas are stronger than others. I'm proud of the fact that RTG is the strongest. The cardiac rhythm heart failure group I worked in before, and Chandra, my boss, worked there as well before. That's when we did the example I talked about with the vanilla food, and we helped that group with leads and with the micro development. And that group is probably the second strongest, and I like to think it's partly Chandra and my influence over there that made them the second strongest. The Medtronic acquired or merged with Covidien a few years ago. They're the furthest behind because they're pretty new to this and haven't had as much time on the journey, but they're coming up to speed very quickly. And the diabetes group has come pretty well as well. They've been on the journey the whole time. They were an acquisition, 15 years ago, but sometimes acquisitions still think they're the old company, so they kind of resisted it for a while, but now the resistance is gone and they've been much stronger on it the last few years. So it is pervasive across the company, and very strongly advocated by both our past, our CEO emeritus and our new CEO, and our chief quality officer and our R&D leaders. So very pervasive, but not 100%.
To hear. Thank you again.
Okay, well, thank you everybody for listening in tonight, and thank you very much, Eric, for your great presentation, linking Design for Six Sigma and Bayesian methods, along with Monte Carlo for new product development. I am now going to share my screen again. Just a couple of wrap-up slides to show. So please, when you do get a thank you letter for participating from our Voice of Customer Chair, Bill Hoddy, please do complete the event satisfaction survey. It's very great information for us, the section, but also for our guest speaker. What things you like best, maybe some suggestions for improvement. We certainly appreciate and desire your feedback. And when you receive that thank you email, you will also get your RU certificate with that. Just a reminder, next month we are meeting on the 3rd Thursday night because of the July 4th holiday and all the people stuck at home during the COVID. We as a leadership team just thought, well, let's err on the side of caution and move our program meeting out a week. So next month it will be July 16th, the 3rd Thursday evening. And our guest speaker will be Marilyn Wheatley from Minitab. She'll be giving a demonstration of Minitab's Six Sigma capabilities as she walks through a Crayola case study. So should be a very interesting and informative presentation, not only on Minitab, how to use it and tricks and tips, but also an actual case study from Crayola. Thank you again for your attendance. Be safe, be healthy, and join us next time.
Hey,
Thank
Bob.
you. Yes.
One last. So for
Thank you.
RU credits, should I email Bill Hoddy, or will the attendees automatically get the RU?
They will get the RU for tonight's meeting directly from Bill Hoddy based on the attendance list.
Okay.
So if you haven't received one for the past, you can either wait for tonight's and then you'll have Bill's email address, or go ahead and use the email that's in this slide deck and request.
Sure. Thank you.
And just again, this is being recorded, so if you have friends or colleagues that you think might be interested in hearing more about this, they can send us a link at ASQ 704 contact us at gmail.com. Link is in our newsletter as well as on our website. Requesting a link to the recording, and we'll send that to them, and then they will get an RECU certificate for that as well. So thank you very much, everybody. Have a great evening.
Thank you.
Thank you.
Thank you. Have a wonderful evening.
Thank you.
Thank you, Eric. Thank you.